the relational nature of public life, the linguistic modes through which people express themselves, and the technological affordances which shape digital discourse. Today, Sarah will be speaking about Choose Your Own Adventure, Computational Social Science. Please join me in welcoming Dr. Shugars.
Thank you so much for that incredibly kind introduction. I'm really excited to be with you all here today. I'm sorry that I can't be there in person. Life is complicated these days, but I'm glad that the power of technology makes it possible for me to join virtually. This is a talk that I feel like it's kind of an amalgamation of things I wish people had told me when I was in my PhD program. So hopefully it'll be helpful to you as well. So I titled this Choose Your Own Adventure, but I also wanted to start by thinking about what is computational social science and why am I talking about choosing your own adventure in it? So, oh, and I will also say the title, of course, draws inspiration from a series of books I used to read in the 80s, although the secret was you could skip to the end and then figure out what the best ending was and work your way backwards. Unfortunately, in science, you can't do that. You don't know what the possible endings are. Recently, I've been playing a lot of Tears of the Kingdom, and I think in many ways that has a similar type of feeling to the Choose Your Own Adventure vibe I am going for here, where it's sort of an open world game and you just explore and see what's out there. And there's so many different possibilities and so many different directions to go. It can feel really exciting, but also kind of overwhelming. So in the context of computational social science, there are many definitions that I'm sure you've encountered in your lives and over the course of this week so far. In general, I think of computational social science as being sort of a toolkit of things that you can use. I would also argue that it's an ethical orientation and that there's a strong ethical component to doing computational social science. I won't touch on that too much today, but I'm happy to discuss that further if that would be helpful. And with this computational social science toolkit, you can use it to really create your own research approach and pipeline. So you're not necessarily following some sort of predetermined path of ways to do things, but you're sort of creating the actual path as you go in a way that I think is fairly unique to computational social science as opposed to other fields. So this can be really exciting. There are opportunities to ask new types of questions that we couldn't ask before, given sort of previous computational capacity and data limitations. And we can also ask questions in new types of ways. So there's a lot of new and exciting things that we can do, but it's also really daunting because you make the path. So there's not sort of a set road set out in front of you. You kind of have to explore and figure out where you're going. So I sort of continually find that this is both exciting and scary because sometimes life is just easier when you know where you're going or you know what the steps are. But a lot of times in computational social science, you're sort of figuring out what the path is as you're going on it, which I think can be sort of an extra layer of challenge. The other thing I wanted to mention sort of in starting this talk, there's this idea of the fox and the hedgehog, and it comes from, there's like a clip of an old ancient Greek text in which somebody said, a fox knows many things, but a hedgehog knows one big thing. Later, a philosopher turned this into a whole book and wrote a whole book about foxes and hedgehogs. And the idea is essentially that the fox is a generalist who knows lots of things, but like kind of, they're just okay at those things. They're not, the pinnacle of success at those things, where the hedgehog knows one thing, but it knows that one thing really well. And the person who originally told me this story was an academic, and he told the story and was like, oh, and of course we all want to be hedgehog. We all want to be like, a superstar at that one thing. And that comment sort of surprised me and really stuck with me because I guess given this metaphor, I've always considered myself a generalist and always thought of myself, I guess, as more of a fox in this metaphor. And I like that approach. And I think interdisciplinary work is very important to me. And part of that is sort of having this more generalist approach where I'm sort of learning different pieces of information and bringing pieces of different fields together in new and exciting ways. So again, it's sort of exciting, but also daunting. And I mention this in part because I think, for anybody in academia, but particularly if you're in computational social science or doing interdisciplinary work of any kind, it's really important to sort of, for your own mental health and well-being, to continually remember that it is literally not possible to know all of the things. The hedgehog might be a superstar at one thing, but the hedgehog is not a superstar at everything. And so I do think that this metaphor is sort of helpful in thinking of, there are some people who I would say are more specialists, who know one thing really, really well, and academia sort of traditionally has trained people to know one thing really, really well and to become specialists. Generalists know lots of things reasonably well, but not necessarily, they don't necessarily know any one thing as well as the hedgehog knows one thing. And interdisciplinary work is really sort of where generalists thrive in sort of being able to understand these different things and bring them together in new and exciting ways. And one of the fantastic things about collaborations and co-authorship is you can have people who have different areas of expertise and whose expertise really complements each other in exciting and productive ways. I mention this in part because I think one of the other challenges of doing computational work and interdisciplinary work is that if you surround yourself with really smart people, those people will always know things that you don't know. And it can sort of be hard to be in that position and feel like everybody else knows more things than you know. But it's more accurate to say they just know things that you don't necessarily know in the same depth that they know. But I do promise you, you too are one of the smart people that other people are surrounding themselves with. So even, when you have those moments where you look around and you're like, oh my goodness, everybody else knows more things than I do, understands things better than I do. It's, quite possible that, certain people know certain things in more depth than you do, but that doesn't mean that those people are smarter than you or better than you. People just have different areas of expertise. And it's really by bringing that expertise together that we sort of can collectively do better science and better research. So this is my spiel about the fox and the hedgehog. It is okay to be a fox. I also want to say, I think often when I talk to people and they talk about, being good at science or being good at computational social science or being good at coding, they sort of imagine that there's some, state that they reach where they're like, okay, now I am a computational social scientist. And when I sit down and I do research, it looks like this, where there's, lots of obstacles going on, but you're dodging those obstacles, doing it expertly, whatever. But the reality is, doing science often feels a lot more like this. No matter how, I like Zelda a lot. But this also is just like, so no matter how much practice you have, no matter how much time you spend doing this work, you're constantly going to have errors in your code. You're constantly going to have issues that you run into. Nobody sits down and plans a research project and executes it perfectly from beginning to end. You're sort of constantly failing along the way. And the secret isn't to sort of play through the game perfectly or execute the research perfectly on the first try, but it's to sort of ensure that you can always go back to the last save and you're sort of constantly making incremental progress, but you die many times along the way, metaphorically speaking, at least. I also want to acknowledge, particularly in thinking about computational work, there is unfortunately a lot of gatekeeping in this space. I think less in computational social science, but sort of in computational fields more broadly. There are a lot of people, I have been given the advice that I shouldn't explain things well, because if I explain things poorly and people don't understand it, then it makes people think I'm smarter. I think that's terrible advice. I don't like to follow it. But it is a thing that is out there in the ethos. So I also wanted to assure you that if you don't understand something, whether it's something in a talk, something you see over the course of this program, something you run into in your future life, it is not a reflection on you or your intelligence. It's really a reflection on the communication skills of the person who is trying to do that explaining. Sometimes it might be sort of malicious in nature, where people are sort of intentionally trying to make things sound complicated to make themselves feel smarter. But a lot of the time, to sort of keep going with my fox and hedgehog metaphor, a lot of the time, if there's one thing that somebody understands and that's the thing they know really well, they'll have a hard time explaining that thing to somebody who doesn't know the context and the details as well as they do, and they don't necessarily have the skill or the ability to communicate it to a broader audience. And it's not, again, a reflection on you or your intelligence, it's more of a communication gap. So once again, it's okay to be a fox, it's okay to know things, little bits of things, and sort of bring pieces of information together in new and exciting ways. So all of that being said, here's my hottest take about computational social science, which is that computational execution is the easy part, but theory is the hard part. And I wanted to say this explicitly because I think often, when I meet people who are getting started in computational social science, there's often, a fear of math, a fear of coding, things like that. But I do want to assure you that sort of the coding part and the computational part is relatively easy. Computers are very good at calculating things. A lot of the methods that you'll encounter, there will be people who've sort of already done the hard work of coding it, and you just kind of have to implement somebody else's method. I don't want to downplay this. There is a learning curve. You do have to learn the syntax and learn how to do it. But once you sort of learn the basics and understand sort of the process of coding, you can always look up syntax, you can duplicate syntax. I, to this day, still Google things. I still get error codes. Like, debugging is just part of the process, and that's just the way it is. That being said, I think the harder part of doing good computational social science is making well-informed researcher decisions. So thinking through questions of, why are you making a certain choice about what data you collect or what model you use or things like that really requires having sort of theoretical motivation for why those decisions make sense. And that can be really hard to do. And this is the part that, you will sort of continue to learn this over time, and it is a lifelong pursuit. So this is something that, I'm still working on improving how I go through this process and figure out what decisions to make. And often when I do research, when I talk about my work at conferences or things like that, a lot of it is sort of going through this process and being like, so I made this decision for this reason. Does that make sense? And sort of, getting feedback from other scholars on these things. The good news is that this part, which I'm arguing is the harder part, is exactly what your PhD training is for. So it's great to come to workshops like this one and learn coding and learn sort of specific skills around the computational piece. But this much bigger piece of sort of learning how to think critically and learning how to approach a data set and approach research questions is what you'll all be doing through your PhD training. So you're already really well set up for success in this space. So all of this is to say, it's okay to take a nonlinear path. As you might have seen already, this talk kind of has a nonlinear path. But I think it's good to sort of explore in new and creative ways and just sort of see where the world takes you. So now that I'm 15 minutes into this talk, I will give an outline of what I will talk about for the rest of this talk. So I've already given some inspiration and hot takes. I want to talk a little bit more about sort of how I like to think about data, and particularly in the context of machine learning. Again, these are the kinds of things that I sort of wish somebody had told me these things when I was starting out in my PhD, because I feel like I often thought that computational approaches in machine learning were much more complicated than they actually are. So I'll go through some high-level intuition, and then I'm going to give a bunch of examples talking about classification and clustering, and then also a little bit talking about text as data. Now, I know this is many different things that I'm going through here, but again, I want to emphasize this is a talk that's designed for foxes. So I don't expect you to walk away from this talk knowing each of these methods in great detail, but my hope is that through this talk and through these examples, you'll start to see some of the underlying intuition that is really shared across all of these different approaches. At the very end, I'll also talk a little bit about validating models, which is a particularly important thing to do. I would pause for questions, but I feel like this is kind of an awkward format, but people have questions like wave or shout or something. Okay, so to think about data, and particularly in the context of machine learning, we can start by imagining a simple data set. So we have a bunch of observations, we have a bunch of variables about those observations. So maybe these are people and their survey responses. Maybe I study a lot of social media, so it could be tweets and then information about the tweets, like what words are in them, how many times they were retweeted, things like that. I'm sure many of you have seen many of these spreadsheets or many of these data frames, so apologies if I belabor the point here, but I do think it's sort of a helpful setup. When we see a set of data like this, each row tells us about a given observation. So for example, this row is telling us information about observation A, and each column is telling us information about a given characteristic or a given feature. So for example, this column is telling us information about variable 1 or just var1. So if we wanted to get a bit more mathematical about this, we could talk about this data set as being a matrix or a collection of vectors, where really a matrix is just a spreadsheet without the row or column labels. The benefit of that is now we're just looking at the sort of mathematical values inside, and we can treat it as a mathematical object. And a vector is another type of mathematical object, which in this case would be a single row or a single label or a single column. Again, we're sort of ignoring the label. So for example, this vector describes the features of a single observation. In this particular case, it's the features of observation A. We might call this an observation vector because it is describing a certain observation. We might also call this a vector, and this is a vector that describes a single feature over all observations. In this particular case, it's variable 1 and describing that variable over all of our observations. So we might call this a feature vector. And so when we think about a matrix, what's helpful about it is that it's basically simultaneously describing all our observations and all our features. So it's just a very compact way of formatting that data. And again, I'm sure that you've seen many of these sorts of tables. I always felt like a matrix sounded like a really scary or like a big thing. But when you think of a matrix, really just think of like a spreadsheet and just the data in that spreadsheet. And at its core, machine learning is really about looking for patterns in matrices or in spreadsheets. Alternatively, we might think of this as sort of looking for patterns in quote unquote high dimensional space. So I will explain what I mean by that as well, because this is language that's often used when people are talking about machine learning. They'll be like, oh yeah, my model has, is 300 dimensions or whatever. So n dimensions, an arbitrary number of dimensions. Each of those dimensions would be sort of a feature or a characteristic about an observation. So imagine we have a very simple data set or a simple feature matrix where we've got 4 observations and just 2 pieces of information about each of those observations. Essentially, we can think of this as describing our observations in 2-dimensional space. So each of these sort of pieces of information about an observation describes an observation in this 2-dimensional space. We could do this in 3 dimensions as well, although it starts to get harder to visualize in 3 dimensions. And mathematically, we could do this in an arbitrary number of dimensions. So if you have, 100 survey, there's a survey that has 100 questions on it, you've got 100 pieces of information about each respondent, you could sort of consider those as where these people exist in some 100-dimensional space. You can't plot that because brains don't work that way and visualization doesn't work that way, but a computer could take that and be like, ah, yes, this is a 100-dimensional space. And a lot of machine learning, again, is sort of based off this intuition that we're thinking about how our observations, sort of where they fall in this n-dimensional space described by the features or the pieces of information we have about those observations. So the core intuition of machine learning is that we're looking for patterns in this n-dimensional feature space, where n is essentially the number of pieces of information we have about each observation. So patterns means looking for observations that are similar. Sometimes it could be looking for observations that are sort of close together in this feature space, and we'll see some examples of that. And when I say the word features, sometimes these will also be referred to as IVs or just X. sort of used interchangeably depending on exactly sort of which field you're in or which subfield you're in, but they all essentially mean the same thing. It's sort of input that you are given pieces of information about your observations. So whenever we're doing a machine learning task, we generally want to start by asking questions about what matrix or what vectors do we want to work with. And of course, the answer to that will depend on a research question. So a lot of the work, and I think, again, this is sort of the harder part of doing computational social science, is figuring out like what data do we even need to begin with. Sometimes, particularly if you're working with trace data, it might be, okay, we have this data, and then the question is more of what does this data actually mean? How can we interpret this data? Can we use this variable as an indicator of some phenomena that we're interested in? And that sort of is the theory part that goes into setting up your model, where once you have your data, you'll want to think about sort of which of these columns or what pieces of data, if you're collecting data, what pieces of data do you want to collect that will be input to your model, and what pieces of information, if any, will be output of your model. In general, you have to have at least one piece of input, but you can also have many. This would also be sort of describing how many dimensions you're working in. In terms of the output of your model, I'll talk in a minute about the difference between supervised learning and unsupervised learning. Typically with supervised learning, you would have one piece of information as an output, sort of a Y variable or a DV. In unsupervised learning, you typically don't have a DV, and you're sort of looking for patterns just within the X data itself. So again, I would argue that the sort of harder part of doing this work is identifying and collecting your data, or choosing what features and measures are sort of best capture the phenomena that you're interested in. Again, this is sort of the theory part of the work, and it takes a lot of practice, and is sort of, it's the piece of the work that as you develop a research agenda, you'll sort of, no matter how senior you get in your career, you'll want to get feedback in the choices that you're making in terms of collecting your data, interpreting your data, things like that. This is the harder part. And then also sort of identifying the methods that are most appropriate for answering your research question. And this is where I think it can be very helpful to be a fox and to have sort of information about lots of different types of methods, because even if you don't sort of initially know those methods in depth, if you know enough to be like, oh yeah, there's a method that kind of does this, then you can go and like learn more about that specific method and see how it applies to the specific problem that you're solving. It is very hard, if not impossible, to learn every sort of machine learning approach without having a specific problem that you're trying to address. But just sort of knowing approaches exist and sort of having a general sense of sort of how these approaches generally work, if one of them, that gives you enough information to determine if something might be applicable to your particular research question, and then you can sort of do more research or experimentation around that particular thing, or find a co-author or a collaborator who is an expert in that particular method and start working with them, or asking if that method makes sense for what you're trying to do. All of that being said, I think the easy part is then executing those methods. I do want to acknowledge again, it does take a lot of trial and error. There's definitely a learning curve here. But once you sort of get the basics of coding and syntax of various languages, a lot of these methods can really be implemented in a couple of lines of code. And it's sort of, the implementing is the easy part, but figuring out what your data should look like and then also interpreting the results is really the hard part of doing this type of work. Okay, so that's sort of my overview of my intuition around data, particularly in the context of machine learning. And now I'm going to go through many different examples of machine learning algorithms. Again, I don't expect you to learn these in depth, but I want to sort of illustrate this point that all of these methods really focus on thinking about our data as sort of describing observations in high dimensional space, and then sort of doing slightly different things with that. So I had promised I would say more about supervised and unsupervised learning. As supervised learning in general, we know both the input values and at least some of the output values. And then we learn from our known Y labels and we'll predict unknown Y labels. So regression and classification are both common examples of this, and I'll show a more detailed example in just a minute, so it makes a little bit more sense. With unsupervised learning, you typically don't know or even have an output, and you're trying to learn sort of the general structures or relationships in data. So clustering and dimensionality reduction are examples of this, and again, I'll sort of show a more concrete example in a few minutes. I'm not going to talk today about reinforcement learning, but I did want to mention that this is sort of another branch of machine learning that exists in which you can sort of give rewards for models that perform well and then train sort of a better performing model essentially. So to talk a little bit more about the difference between unsupervised and supervised machine learning, I like to use classification and clustering as examples, where classification is sort of one of the classic machine learning approaches, or sorry, supervised machine learning approaches, while clustering is one of the classic unsupervised machine learning approaches. But in many ways, these approaches are both doing very similar things, just in slightly different ways. So in a classification task, which again is a supervised approach, you know specific classes or specific labels that you want your observations to have. Whereas in clustering, you typically don't know exactly what those clusters will represent. So for example, a classification task might be something like, I have a bunch of emails and I have emails labeled as either being spam, important, or random, or like everything else. And I want to use these known labels of spam and important in order to predict for a new email if that new email falls into a spam bucket or an important bucket. For classification, or sorry, for clustering, again, it can be sort of a similar problem, but here I would just be saying, oh, I want to see what emails are similar to each other. And then I would assume that natural clusters that emerge sort of highlight important dimensions of difference. So I don't necessarily know that there will be a spam cluster or an important emails cluster. I'm just kind of assuming if I look for clusters of emails that are similar to each other, maybe I'll end up with, okay, here are my emails around SICSS, here are my emails around other teaching obligations or whatever, and I sort of find different clusters where I don't necessarily know going into it exactly what the labels of those clusters will be. Another example of clustering would be saying something like, I want to find out what shows are similar to each other so I can find out what to watch next. So you don't necessarily have sort of specific labels or clusters in mind. You just want to know, like, what are the shows that are similar to the shows I've already liked? The classification version of that would then be something like, I want to predict the genre of a new show based on its similarity to existing shows of known genres. So I might go into it saying, okay, here's a list of 10 different genres. And for a new movie that you give me, I want to figure out which of these 10 genres or which of these 10 classes it sort of falls into. To put this in a bit more of a visual way, we can think of classification as we have data where we know sort of both the input and the output values, but then we also have data where we don't know sort of what labels we want to apply. And we want to use our known information in order to understand what labels to apply. For clustering, on the other hand, we just have sort of our raw data, and we want to look at that data and find if there are natural patterns existing within it. So I'll go into a little bit more depth in sort of a particular mode of classification. So for classification tasks, usually the observation can be assigned to some category or class. This can be binary, so it can be a true or false thing, or you can have multiple categories. Maybe there's 10 genres of films or 100 genres of films. Either way, a classification task will have a discrete DV or Y variable. So there's sort of a set number of buckets that you are assigning each observation to go into, and each observation goes into a bucket. You can have multiple sort of features or attributes or pieces of information about your observations that then can help you predict which category your observation belongs to. So one of the sort of classic ways of doing this is called k-nearest neighbor, or KNN, where the core idea is that an observation belongs to the same class as its neighbors. Putting this another way, the assumption is that the differences in the various features that we have are descriptive of differences in class or category to which something belongs. So again, sort of with all the examples I'll show today, they all sort of deal with thinking about our observations in some high dimensional space and then using that to find similar types of observations. So all of this is to say, the idea behind the KNN approach is that observations with similar features should belong to the same category, and that observations with similar features will then be close together in feature space. And so if we find observations that are close together in feature space, then we can assume that they belong to the same category. So again, this is all about thinking about our data in n-dimensional space. And the goal is to, if we don't know what a label observation I should have, we'll look at what observations are, what observations are close to I, and then label I based off its neighbors' labels. So to put this a little bit more visually, imagine we have this data set where we've got two pieces of information about each of our observations. I've labeled them X1 and X2, so we're working in 2 dimensions here. As a side note, I would say anytime you're learning a new method, always very helpful to just reduce the problem to having essentially 2 dimensions so that you can look at it visually and go through step by step and see what's happening. I find that very helpful, at least to help me sort of really visualize and understand what's going on. Here, I've sort of encoded the DV or the label for each class as a color. So we've got 3 different categories. Each observation either belongs to category blue, category red, or category yellow. Again, we can think of our sort of pieces of information or our features as describing our observations in space. So we can plot this with X1 and X2 and then see how each of these observations fall. So if we look at this, again, sort of our features provide coordinates for each of our observations. But then the sort of fundamental challenge of classification is, imagine we now get some new data point, I've labeled it M, and this data point appears right here. And the problem that we have is we want to figure out what label should we give to this new piece of information. Should we put it in category red, category blue, or category yellow? Conceptually, it should be in the category that most of its neighbors are in. I've intentionally chosen this point so that it is hard to sort of figure out or see which category most of its neighbors are in. But you can imagine, given this plot, I could have given other points where it would be very obvious sort of which category that new observation should fall into. So essentially, the first thing we have to do is figure out who its neighbors are. There are many different ways to measure distance. I'm not going to go into too much detail, but for now, we can sort of assume we're using Euclidean distance, where we sort of use the Pythagorean theorem to figure out the distance between 2 points. There are many other ways to measure distance as well, but we'll just assume that we're doing that. With many machine learning methods, how you measure distance becomes important because so much of it is about sort of thinking about our observations as being sort of near, close, or far from each other in this high dimensional space. So again, here's sort of the general question that we're looking at. We've got this new observation, and we want to know which observations are close to our star observation. So if we use Euclidean distance, we can basically go through and say, okay, so this observation F is the closest, and I'm just going to rank each observation based off its distance. So the second closest is this observation I, which is down there. The third closest is this observation C over there. And I can essentially go through all of our observations and make a big long list saying how far it is from our new observation. So then k-nearest neighbors, the algorithm would basically take this list and assign a class to our new star observation based off the majority of k neighbors. So If we chose k equals 4, for example, we would look at the top 4 closest observations, and we would assign the class red because 2 of its neighbors have class red, 1 has class yellow, and 1 has class blue. If we use k equals 9, we would assign class yellow because 3 of its neighbors have class red, but 4 have class yellow and 2 have class blue. If we use k equals 5, chaos ensues because we have 2 red neighbors, 2 yellow neighbors, and 1 blue neighbor. In Python, at least, it has sort of an arbitrary tie-breaking rule where it saw red first, so it will assign it red. This is when you start to really get into the weeds of how various algorithms work, and this is the kind of level of detail you don't need to know unless you're doing a specific project with this kind of method. But there are different tie-breaking rules that will exist in different implementations of it. But the basic idea, and again, I sort of purposely chose a hard example here where it's very sensitive to the value of k that we chose, but you can imagine many other data points that could be in here that would not be that sensitive to the value of k and would sort of constantly find sort of the clusters of blue, of red, or of yellow. And then the algorithm can assign a label based off these neighbors. So again, just to sort of contrast classification and clustering, we can sort of use classification to predict the labels, whereas in clustering, we don't have the specific labels. So I'm going to go through this pretty quickly. There are many steps to the k-means algorithm, which I'm going to show in order here. I've got a little data set with penguins because I really like penguins. We're just looking at bill length and flipper length. Don't worry too much about the data, but essentially we're working in 2 dimensions. So we've got our bill length and our flipper length, and each of these data points represents a penguin. So when we do the k-means clustering algorithm, we start by choosing a value of k. I'm going to choose the value of k equals 3, and I'll choose centroids. We choose these at random. The easiest way to do this is to select sort of k observations. You can do different things. These starting points don't have to be good. I've intentionally chosen a bad one here. And then you assign each of your data points to the closest centroid. So starting out here, we get a bunch assigned to the orange cluster, a few assigned to the yellow, the blue cluster, and then this bottom one is actually so close to a different centroid that it has no points assigned to it at all. So it doesn't even have observations assigned to it. Then you compute the cluster, the centroid of the newly formed cluster. So what I mean by that is you look at all of these orange dots and figure out, okay, what is the center in the space of every orange dot? And you can use your favorite distance measure, but basically we move this this orange centroid closer, or like over here. Meanwhile, the blue centroid would move up a little bit because it would represent the center of all of the blue dots. This bottom point won't move because it has no observations assigned to it. Then you sort of repeat these 2 steps over and over again until the centroid location is stable. So again, you assign each data point to the closest centroid and then compute the centroid of the newly formed clusters. So if we look at this, this is just after 1 iteration. We've got a few on the edge here that had been orange from the initial assignment, but now they're actually closer to this blue centroid. Down here, we've got some observations now that are closer to this bottom centroid, and they're sort of defined as purple based off the plot or the legend. So if we then assign those observations to the new clusters, we can start to get something like this after 2 iterations. And then after 3 iterations, as we sort of continue to go through these steps, we're just continually recalculating the center of these things and then assigning each observation to a centroid. And eventually it'll reach stability. In this case, it only took about 20 iterations of the algorithm in order for it to reach stability. So just to show this again, you choose a couple, and there's lots of literature around how to choose a good K. I've just chosen K equals 3. You choose K points, you assign each data point to the closest centroid, compute the centroid of the newly formed clusters, and then repeat those until the centroid location is stable. Now, again, you can do all of this in about one line of code. So it's all like, this is what's happening under the hood. But again, there's not like a specific output variable or a specific label that we know these clusters, that we know are going to apply to these clusters. But rather we're sort of trying to find the sort of natural clusters that exist in the data. So with both of these methods, for both KNN and k-means, you can implement both of these in essentially a single line of code by using sort of pre-existing functions or packages that people have written. But I did want to spend some time explaining sort of how they work and the intuition behind them. And again, sort of to particularly emphasize that they're both sort of thinking about your data in high dimensional space and then looking for patterns or similarities in that data. So I don't have too much time to go through some of the text stuff, but the point here is essentially that we can think of textual documents in much the same way, where we can think of a document term matrix where we have a bunch of documents and each of those documents have words in them, and we can count how many times a word occurs in a document. So again, each row sort of describes a document in the shared feature space or word space. So our feature space is defined by the words we have. And then each column describes a word in a shared document space. And it's essentially this intuition that underlies a lot of text as data types of methods. So this includes topic modeling, where essentially we have a bunch of documents. We want to assign those documents to topics, but we don't know what topics those are. But we do know that each of our documents has words, and we can sort of imagine topics as being things that are made up of words. And so by thinking about this way, we can essentially think of topic modeling as a clustering problem, where we want to look for clusters of words that tend to appear together, and think about documents as sort of having similar clusters or similar topics within them. So all of this is to say that essentially topic modeling we can also think of as like a high dimensional clustering problem. Similarly with word embeddings are sort of based off this intuition of you'll know a word by the company it keeps, or a word which occurs in similar contexts are similar. So we can do a similar type of thing where we can look at a bunch of documents, see how frequently we see words co-occur across those documents, and then use that in order to sort of predict what word might go, like to fill in the blank or something. Again, I'm not going to go through this in too much detail. I know I'm running short on time. So the main thing that I wanted to get to here, again, is that, word embeddings, again, sort of are based off this intuition that words which appear in similar contexts will then sort of have similar embeddings or sort of exist in similar feature space to each other. And you can then use that to do a lot of like interesting and exciting things in terms of comparing words and word use. It can also reflect the bias that goes into that training language, which is, I think, really important and interesting when thinking about the bias of language. Word embeddings are also an unsupervised method. It really relies on word sort of on the proximity of words having meaning, but it is remarkably good at generating sort of high dimensional representations of words. And by high dimensional, I mean the typical word embeddings are around 300 dimensions. So essentially, like for each word, you have 300 pieces of information or exists in some like 300 dimensional space, which again, you don't have to actually visualize that. The computer can do it for you. With word embeddings also, you can train your own models, but again, there are many pre-trained models that exist and have been already trained on very large sets of data. There's this great article by Pedro Rodriguez and Arthur Sperling that talks about word embeddings and sort of the trade-offs between training your own versus using a pre-trained one. Sort of the main takeaway is that in most contexts, pre-trained models work just fine. And again, you can sort of implement these pre-trained models in a few lines of code. So I know that was a very quick overview of word embeddings, But again, I just wanted to emphasize that it's all about sort of thinking about your data and thinking about a document in some high dimensional linguistic space, and then using that in order to basically be able to do math with it or have your computer do math with it. So before I wrap up here, I also wanted to say a few words about validation. Algorithms have big golden retriever energy. They will return results, even if those results do not make sense. And so, just like me, your models also will always require validation. There are two basic ways in which to validate a model. One is you can start with hand labeled data and see how well your model does. So this is sort of the approach that's often used for supervised methods. Or you can hand label a sample of model output and see how well it did, which is common for unsupervised methods. But either way, you really have to look at your data at some point in your pipeline. In general, we'll sort of test out of sample, particularly in supervised tasks, where we'll split our data set and train on one part of the data and then test on the other part of the data. So if you imagine that we have this data set, we might split it and use just part of the data to fit our model or train our model. And then we have data that we can use to see how well that data did. And that sort of out of sample data wasn't actually used to train the model, which can be sort of helpful in making sure our model works well. There's really no standard procedure for validating or hand coding. People often ask me like, well, how many things do I need to hand code? And that's the $1 million question. It's often a trade-off between how much effort goes into that hand coding. So if your hand coding task takes a very long time, you can get away with having fewer things hand coded. If your hand coding task is a very fast one, you should code it more. In general, you want to do as much as possible, but there's also, obviously a trade-off there. In general, I think particularly in computational social science, when we say like, oh, use machine learning or whatever, it typically means using or adapting an existing model. In many cases, particularly in NLP, image analysis, many other areas, you can use pre-trained models. And this can be really helpful because model training is often very data extensive or intensive. They're often trained on like the entire English language or the entire internet and things like that. So this is part of why validation is so important, is that it's really important to think about how well this model does on your specific data and in the context that you're studying. So as some final closing thoughts, you are free to choose your own adventure in computational social science. Your research is your adventure. It is hard because literally nobody knows how the story ends. Nobody can tell you exactly what path to follow because you are making the path as you go. And that's exciting, but also scary. But I do want to assure you that you are smarter and you're more capable than you probably give yourself credit for. I don't want to assume you don't give yourself credit. Maybe I'm just projecting here, but I do want to assure you, each and every one of you can excel in computational social science. I believe in all of you to do this work and do this work well. And I really, again, I'm sorry I can't be there in person, but I really encourage you to keep in touch. Feel free to reach out anytime. I'm more than happy to chat. So thank you again for having me. And I hope we can do a few questions before we close here.
Oh, yeah. So first of all, thanks so much for this excellent, fascinating, and really engaging lecture. And right now we have 10 minutes for this, I think. So any questions from the room? I think you can directly speak from where you sit and you should be able to hear. Any questions if they're, oh, sorry. I thought that, no, but maybe not, but anyway, oh, sure.
Thank you so much for this presentation. It was absolutely fantastic. My question's about distance measures. You touched about it briefly in your presentation. Is it poor practice if you use different types of distance measures in your research? Like if your spell checker uses Euclidean distance or Levenshtein distance, and then your k-means clustering uses a different one?
That is a really great question. So I would say, and I feel like this is going to be my answer to a lot of questions. It depends. I think as as I'm sure you know, there are many different choices and things that you do throughout your research project. So for example, like, oh, what distance measure does this use? Any answer is okay as long as you have a good and principled answer for why you do it that way. So like, you know, if I'm a reviewer reading your paper, for example, and you say, oh, we use Euclidean distance for everything, then it's sort of an easier argument because you can just, you can either explain why you used Euclidean distance, or you can have, you know, appendices where you're like, and here's 5 other distance measures and they're all the same or whatever. If you say, okay, we use, you know, measure A here and measure B here, again, that's fine, but there should be some reason for like, oh, it doesn't really make sense to use Euclidean distance in this context, so that's why we use this other distance measure. So, you know, it can be fine, but it would definitely need to be explained, I would say.
Yeah.
Perfect. So any other questions? Or if no more questions, I guess maybe people will reflect. I mean, there has been a lot in the content.
Yeah,
so,
I know.
no problem. And I think we're glad that we still have the recording. So we will work on that, how to probably save that recordings for later. And we will yeah. So Sarah, I assume that you'll be fine that if we also leave your email address to participants. So if like anyone who has further questions, you can feel free to reach out, because for this speaker, unfortunately, we did not plan for a one-on-one session for them to talk with you. We usually do that for other speakers, but I think it's very nice of you to also offer this opportunity to meet them, maybe potentially virtually on Zoom. So I will do that. And then thanks again for your great lecture and your virtual joining of this session, this event. Okay, thank you.
Thank you.
Yeah, thank you. Great to see you all. And please do reach out. I'm more than happy to chat.
Sure, cool, perfect. Okay, now I'm going to start Zoom and bye.
Bye.
Okay, everyone, feel free to go and I think